Hi everybody, welcome back to the lab. For those of you who have been patiently waiting, apologies, but it is time for another episode of our power supply project. In previous videos, I have looked at sensing the voltage, the current, driving MOSFETs, regular BJT transistors, voltage references and things like that. And some of the outstanding issues that have been raised by a few of you, and which were also left on my to-do list, were how do you drive a Highside MOSFET up to the maximum rail of your actual power supply core voltage. So say you've got a 15015 transformer at a few amps, and so by the time you've smoothed it and everything else, you've got for argument's sake 30 volts DC available to drive your output, and you want to be able to use all of that. Well, the circuits we've looked at up to now basically haven't been able to do that because a MOSFET or a any really transistor, it requires a certain level of biasing voltage on either the base or the gate of the transistor of a few volts at least. With a MOSFET, it's usually about 4.2 or above. With a transistor, it could be 0.7 volts up to a couple of volts, depending on whether you're using Darlington drivers or something like that. So how do you get around that? And we're going to have a look at that today. We've also looked at using P-channel devices as well, where you actually pull down the base or the gate relative to the source or the emitter to turn them on. And these obviously can work a little bit better in that it's simpler to drive the Highside rail, but they come with their own issues as well. And especially with MOSFETs, which is what I'm going to be continuing the power supply project with, the issue you have there is that a P-channel MOSFET is physically less capable per unit of silicon of driving power loads. So I want to be able to use an N-channel MOSFET. So that's the way I'm going to proceed with this. The other side of things as well, and we've looked at this in the previous videos about the effects of it, is how the sensing of your current and your voltage can be impacted depending on the current you're drawing through your power supply. And what we found is, if you have a low side current sensing where you have a power resistor in the 0 volt rail, basically, it can have an impact, and it's complicated to compensate for this impact of elevating the 0 volt rail above the true 0 volts of the power supply. And in an ideal situation, you really want that 0 volt to be set in stone at the proper 0 volt rail and not be drifting around based on the current that you're drawing through it. And when you start putting power supplies in series and things like that, this becomes even more important, or in parallel, because you can get them fighting with each other and things like that. So you want to really keep that sensing out of the picture if you can. And the only real way to do that is to put the sensing resistor for the current in the Highside rail before you measure the output voltage. This way you completely eliminate the current sense, and you also don't have the current that's being used as part of the measurement circuit interfering with any of the other measurements as well. So it's one of the design objectives that I want to be able to have in my power supply is to use a Highside current sense. I also want to use, as I said, the N-channel power MOSFETs, but how do you get those to go to the full rail? Well, the way that you can do that is to use a separate supply for your analog circuitry and have the 0 volts of that analog supply sitting on the actual power rail of the output of the MOSFETs for driving. That way, if you want a low voltage output on your power supply, then the 0 volts of your analog control circuitry will go down to that low voltage along with it. And as you increase the voltage, then that whole analog rail is going to slide up and down with the main power output. And the benefit of doing this is that you do not need to have operational amplifiers or any other circuitry that's capable of working with a supply that is equal to or in excess of the main power supply, which, if you're outputting 30 volts, then your main supply before that could be, say, 35 volts. And if you have an analog, Highside supply that's allowing you to drive the MOSFET fully on, then you may have as much as 45 or 50 volts sitting above the ground rail, and your op amps and things are going to have to be able to work with that, or you're going to have additional components on the low side and basically use some kind of inversion or elevation logic like a voltage converter to get it up to that high side voltage. But either way, it's a lot more complicated, and I want to try and simplify the way this thing works. So we're going to look at how we can do that as well. I've got a few drawings prepared. So we're going to look at using differential voltage sensing, differential current sensing, high side, and we're also going to look at how we hook this up onto the positive rails of the power supply. And at the end of the day, we're also going to look at a slightly different technique for controlling the MOSFET, because in other videos that I've seen and you guys have seen, and if you haven't looked at it, you know, Martin Lawton on his YouTube channel is working on a student power supply, and one of the things that you'll see there is in order to have the current limiting and the voltage limiting work cooperatively with each other, they're using a pair of transistors, open collector, to dominate either the constant current or the constant voltage, and neither of them can actually push the supply high, but they can pull it low to drive the output stage. And in this particular case, it's using a level shifter in the form of a few transistors to get to the driving of a high side NPN power transistor. I think it's using a 2N3055 or something. What I'm going to do is have the analog supply plus or minus 12 to 15 volts, and I'm going to set the 0 volts of that supply on the analog output, like I said, on the power rail of the supply. So let's start looking at some of the diagrams that we're going to use to do this. Okay, so here's the first diagram I want to go over, and we're going to test this on a breadboard shortly as well, and that is for differential voltage control. We have within our control system, there are two things that we need to achieve. One is to be able to have a set point for the voltage, and I have that represented here with a VSET, and my ideal is to use a 0 to 5 volt control signal, because my voltage reference is going to be 5 volts. So whether I use a pot or an analog to digital, digital to analog converter, or some other kind of control mechanism, either a PWM output with an RC, I want to basically have this thing to be able to be controlled from a 0 volt representing 0 volts to 5 volts representing a 30 volt output on my power supply. So I've got the 5 volts, 0 to 5 volt coming in. All right, now let's ignore this piece of circuitry over here for the moment, and let's now look at the current sensing area over here. So what I have is I have the standard op amp, and we've looked at this before. I've got the sense input, so we're using differential, so we've got 2 of them. And what I've got is one that goes to the positive rail of the power supply and one that goes to the 0 volt rail of the power supply. Now this is the output pins, remember, not the basically not across the smoothing capacitors of the power supply. It's the actual output after any control system has been put in play. Now when you look at this diagram, you'll see that my positive input is actually going to the negative input of the op amp, and the negative input of the power rail, i.e. the 0 volts, is going to the positive input. Now that's perfectly fine for a differential amplifier, and remember, we're going to be driving this amp with plus or minus 12 or plus or minus 15 volts or something like that. Just a standard off-the-shelf kind of split rail supply that you can get relatively cheaply. You can make it with a transformer and a bridge rectifier, a couple of caps, and some low-cost 7812, 7912 kind of voltage regulators will be more than adequate for this. Anyway, so we've got the 2 inputs, and I've got 100K in each one, which means it's going to limit the current coming in here as well. And I have a 22K on the positive rail. It's basically acting as a voltage divider, so 100K and 22K. And on the negative rail, there is obviously some feedback with the 22K as well. So this is all balanced as far as values are concerned, which makes the math easier to figure out. Now I've just been using an online calculator to just do this, because it's a lot simpler than trying to type it all into a spreadsheet or something else to figure this out. Anyway, the net result of what we have here, again ignoring the summing, let me just cover that up just so we don't confuse, is that we have a gain of about 0.22. So that means that for 22 volts coming in, will have basically just over a fifth of that coming out of the other side. So we've got 0 to 30 volts coming in here, which is what our desired range is. Based on this configuration, at least mathematically, we're going to get a 0 to minus 6.6 volts out of this differential circuit. The negative output is because, one, we have a split rail, so we can go negative, and the second part is, remember, we've wired these up backwards, so the positive input is actually going to the negative of the differential op amp. Now, you might be saying, why the heck am I doing that? That doesn't really make sense, except that when you look at the consideration of what I'm doing with the set point from our potentiometer or digital to analog converter or whatever our control system is, then it'll make it very clear. So what I'm doing here is I have a summing junction simply made out of a set of resistors, and the junction of the two is basically the difference between the V-set point, which is our potentiometer, DAC, whatever, and the output of the sensing. So the output of the sensing is going basically from 0 to minus 6.6 volts, and the input from the V-set is going from 0 to plus 5 volts. So what we want to do is, simply using resistors at the junction of the pair, we can actually get the difference. So if this is sitting at, if I was having 100K on both sides, where it's a 50-50 split, this would be sitting at, say, minus 5 volts, and this would sit at plus 5, so the junction would be 0 volts. Now, you might be asking, well, why didn't I just make the gain of this to be exactly the value of 0.2, would it be 0.2? 6. Like a divide by 6, rather than the value I've got and have it as 0 to 5 volt output. The reason for that is because I've picked standard resistor values out of my resistor set. I have a standard 35 resistor box of resistors that has all these standard ranges, and they're all about 5% tolerance. And what I wanted to do was not have to go and buy any particularly expensive precision resistors. I wanted to just use off-the-shelf ones, and so the way that the math worked out, I would have a gain here of 0.22, and the output would go to minus 6.6 volts. Now that's not an issue, because even though my input is ideally 0 to 5 volts, I've got a standard 100K here, and all I've done is made the other side of the summing junction 132K. So we end up with ideal values of a 0 output for a plus 5 in here and a plus 30 volts here, giving us the minus 6 here. If you do the math with this little simple divider network, you'll end up with 0 volts coming out of here. So that's what we're going to do for the voltage control. It's all very simple, and I will inject a little bit of going through the math into the video as well. So let me just bring up the website that has this calculator on and just basically show you. All right, so now let's go and have a look at the current control side of things and see what we're going to try and design there. Okay, so this circuit looks almost identical to the voltage side of things, and it basically is. We still have our ideal 0 to 5 volt set point for the current coming in here, which is going to be from our DAC or from our potentiometer. And we have the same positive negative sensing inputs, but the difference here right away is that I have a 50 milliohm resistor here, and this is what is going to develop the voltage that we're going to compare to for our set point. So 50 milliohms, our ideal power supply, what I'm working on for the sake of this, is 0 to 5 amps output, which means with 50 milliohms, that's going to give us a 0 to 250 millivolt differential across this. Now, I've got this marked as plus for red and minus. This is with reference to the current shunt resistor that we're using. We're going to use a 4-terminal Kelvin shunt resistor from Vishay for this. They produce some very nice ones, and I have a few samples here that we're going to use today. And the thing to note, though, is that this positive input is not the positive output of the power supply. The negative side of this shunt is the positive output of the power supply. When we look at the full circuit, you'll see what I mean there. But at the moment, what's going to happen is we're going to have our current flowing in through the resistor and then out. So because this is high-side sensing, then this is the inside the power supply, if you like, and then this is the negative side of the current measurement, which is the one that's actually going to go to the output of the power supply terminal. All right, and our voltage sensing would basically be tapping on this particular point here in order to measure our output volts right on the output terminal of the power supply. So having said that, let's just get by that now and look at how this one is working. And it's basically exactly the same as before, but obviously different values. So I have standard 10K resistors on the input, just to keep them balanced. And what I have is, this is basically acting as pretty much just a voltage follower with a gain set on the negative feedback. So remember what I said, this is the positive side, this is the negative side. So the output's going to swing negative for the difference here, and the gain is basically set in this case. It's not really a full differential sense in the same way as the other one was, because the positive side does not have a resistor going to ground. It's just basically going to be this negative input part is the low side. So as this varies, the output is going to try and do what it can do to keep this side at the same value. So it is working as a differential amplifier, but in just a slightly different way. And we've got the gain here based on the 180K resistor and the 10K resistor, giving us a mathematical gain of exactly 19. So the gain is calculated by 1 plus R1 over R2, this being R1 and this being R2, which gives us 180K over 10K, which gives us 18, and then plus the 1, which is basically the fact that you use for this kind of circuit, giving us a gain of ideally 19. Now, the gain, I'm using standard resistor values here, so that you can pretty much pick up your resistors from wherever you need to. You can make it more precise if you want to, that's fine, but for the sake of this demonstration, I'm just using off-the-shelf standard 5% parts. We'll go into more of why that doesn't matter too much later through the video. So 250 millivolts input, a gain of 19, gives us an output of 0 volts to minus 4.75 volts. All right, now that's not ideally 5 volts, and as I said, I could play around with changing the gain here, maybe putting a resistor in parallel with a 10K or something like that, but there were no easy values of the standard off-the-shelf resistors that I could get that would give me exactly the gain that I want for this. Okay, so what I'm using now is I've got the 0 to 4.75 volts coming through a 22K summing resistor here, and I've got a 22K and a 1K coming from the 0 to 5 volts, gives me 23K. So the difference here at this point allows me to have the minus 4.75 volts representing the 0 to 5 amps, and the 0 to 5 volts, which actually there's a slight discrepancy here. This is the ideal that I wanted to be able to use, but mathematically with these values, it basically worked out to be 4.97 volts. So very, very close, and you don't have to worry about that, because if you're just turning a pot, you're going to be adjusting it until you get what you want. And if you're using a DAC or something like that, then you can compensate for these variances in software. So that's one of the reasons why the resistor values themselves don't particularly matter. What matters is you have them balanced so that the mathematics and so that the gain and everything else works out correct. And also, if you get them all from the same batch, so try to keep them the same. Try to keep the resistor values matching. So if I want 22K here, if this is slightly higher, then this is slightly higher. If they're from the same batch, they're probably still going to be sitting within a certain range of each other. But as I said, you can compensate for that if you need to. What is more important with these components is that they are overall that the system is thermally stable and stable over time as well. You don't want them to be drifting in a way that would increase your errors. So with a differential amplifier, normally because both sides have the same values in it, they usually compensate for each other. So they'll move around, but they won't really change things too much, because the feedback and the input resistors and everything else are all of the same kind. There will be some discrepancy, but it's all about how much money you want to spend. And right now for this demo, we're looking at keeping the price down using standard off-the-shelf parts, but getting a very usable power control system set up. So here's our, as I said, here's our differential current measurement. We've got a gain this time instead of a division. The other one was 0.22 gain. This one has got a 19 gain because we've got low voltage. We want to go to a high. So and the other reason we want high voltages here is you've basically got more control over your output, because if you've got a large swing, you don't have to have as much gain in later stages to control things, and you can have a much more stable power supply, right? So anyway, here's our summing output, just to finish this piece off. And so 0 to 4.97 volts in as our voltage reference to set the current, and 0 to minus 4.75 volts here. By the time we get the summing with a 22K and a 23K, they balance each other out, so that if you've got your 4.97 volts on your iSet and you've got exactly 5 amps running through your shunt resistor, then you're going to get 0 volts on your difference output of the current control circuitry. Now, one of the things to remember with this current control circuitry, and also with the voltage control circuitry, let me just move it across a little bit so you can see the summing junctions. As you can imagine, this is 100K and 100K, all right? You can't load this with something, because you're going to offset the output here. So whatever you put on this sensing pin for the difference has to be high impedance. Otherwise, it's going to offset and imbalance the summing junction of this. And the same goes for the current one. We're using lower value resistors here, but this could equally be 220K and 220K and a 10K, all right? It's the ratios of them that matter at more than the actual values. But if you go too low on your values, obviously your system is going to be drawing a lot more current. If you go too high, then it's going to be more susceptible to noise. So, you know, my voltage one, I've just got higher values. It just happened that the math worked out well and I had them. The current one, I'm using 22K, so it's about a fifth of the value, but they're still high enough that it's not going to make a huge difference on the current consumption. So we've got these two outputs. Now the question is, what are we going to do with them? All right. And what we're going to have a look at after I'm going to go to the breadboard first and show you these two things working, and we'll see how well they actually meet up, the mathematics meets up with the practice. So we're going to do that in a moment. But what I wanted to quickly show you was what we're going to do with the output stage. All right. So here is a very, very simplified view of our MOSFET N-channel driver. Okay, we've got the N-channel MOSFET here. Let me just up that just a touch. We've got our N-channel MOSFET. This dotted side represents the power coming from our rectified, smooth, raw, high current supply, high powered supply, and the solid line is what represents coming out of the MOSFET. Now, between this and the actual output terminal of the power supply is going to be our current sense resistor. Okay, so I haven't got that there because it's not relevant to this particular diagram. For an N-channel MOSFET, you need to drive the gate high with reference to the source. Now, because this wants to be able to go up to full saturation, so if you've got 30 volts here, you need 30 volts over here, then you need at least 4.2 volts or thereabouts above source in order to start turning this MOSFET on. And you don't actually have to go too much higher than that to get it saturated, but you need to be able to control it. So how are you going to do this? Remember, in our earlier videos, we had our op amps basically sitting across the supply. So between ground and this point, we had, so that was say 35 volts. You had to have op amps that were capable of working with 35 volts or 40 volts or more, depending on what your output wanted to be. But the problem with those circuits, and some of you have tried this and seen the same thing, is that you can only drive up to about 1 volt less than the rail. Most op amps, even if they go rail to rail, if you only go up to say 30 volts here or 35 volts, and you've got 4 volts odd or 5 volts drop across here, then your output is never going to be up to this rail. It's always going to be about 5 volts less than what you've got here, because you just can't drive it high enough. All right, so you're going to lose. You're never going to be able to drive this into saturation to the point where this is actually up to here, all right? Because of that situation. So how do we get around that? Well, what we do is, here I've got a 10K. This is just because you got a capacitive load here. I'm just using a couple of resistors just to provide some noise immunity and things, because I have seen, due to capacitive loading, that these can break into oscillation as well if you're not careful. So we've just got the standard 10K, which is what I've used before to drive the MOSFETs, and I've got a number of diode junctions coming out of here. All right, these are just standard 1N4148s or 1N4001s or something like that. It really is not critical what these are. There's not going to be a lot of current flowing through here. And then on the other side, I've got the plus 15 volts, which this would be from our analog supply that we're using to drive the op amps and things like that. And I'm using just a simple 9-volt Zener diode and a 10K current limit just to make sure that the voltage at this point really doesn't go above about 6 volts, okay? This is going to limit any current because there are issues that you don't really want to take the gate voltage too high on the MOSFET so that you don't damage it. So this just provides a little bit of a voltage drop to this control point up into the MOSFET. Now these 3 inputs here, these can be driven by a control system. They can pull, because of the direction of the diodes, you can pull them down, you can't push them up. So if you've got your voltage control coming into here, all this has to do is come basically below the, this is plus 15, so you've got about 5-6 volts here. So this point is 6 volts. So as soon as your voltage control into here goes below the 6 volts, plus this, so let's say 5 volts for argument's sake, you're going to start conducting current and you're going to start pulling this down, which means it's going to start turning this off. All right. None of these things here, the inputs can turn it on. They can only actually turn it off. And so the same for the current control. It's exactly the same. It can pull it down and turn this off, but it can't push it up and turn it on. And if you look at a lot of the circuits that you've seen, even on the Martin Lawton's student power supply, on some of our earlier circuits that we played around with as well, we've had the same thing there. Because you want to have a voltage control and a current control, if you've set, say, 50 volts, sorry, not 50 volts, let's say you've set 25 volts for your voltage limit, and you've set your current to be 3 amps, but your load is only drawing, say, 2 amps, then your current control is going to start driving higher because it says, oh, I'm not actually balanced on my current. I want to increase the drive so that I can get to my current and balance my op amp. Well, if you've got your voltage set to 25 and your current is now trying to get your 2.5 amps or whatever, it's going to try and push this up and turn this on higher. And of course, then your voltage control is going to say, hey, I can't have that. That's exceeding my voltage. And it's going to start pulling down and it's going to fight it and try and keep the voltage. So these two are actually going to be fighting with each other and continually adjusting this, but never really being able to get some collaboration where it says I'm in control for voltage or I'm in control for current. And what you really want to be able to do is whichever one has started to take control, it needs to be able to dominate the drive of the output stage. So by having these diodes, it means that they can turn the output stage off, but they can't force it on. So if you're at a current limit of, say, your 2.5 amps, then this is going to hold it at 2.5 amps. And the only way that this output is going to be able to be changed from that 2.5 amps is if your voltage control decides it wants to be making the output voltage less than the voltage required to deliver the 2.5 amps. So as it comes down, it's going to pull this MOSFET further off until the point, say it's a 2.5 ohm resistor, sorry, a 1 ohm resistor as your load. That means you've got 2.5 amps flowing through it and you've got 2.5 volts on it. Once you get, say, this comes down to trying to get the volts to, say, 2 volts, then this will start dominating the drive here, and this one will actually start trying to push up because it's no longer getting its current, but because of the diode, it's not going to allow it to go up, so the voltage is now back in control again, which is exactly what you want to happen. All right, now if I obviously change the current limit to bring that down further, then the reverse will happen. The voltage control is trying to make it at 2 volts, so it's going to leave 2 amps flowing through. The minute you start bringing the current setting down to something below 2 amps, then it's now going to pull down low instead of going high. And remember, these are differential when you've got split rail, so it's very easy for these things to be able to go below 0 as well as above 0. And it's going to start pulling this down, and it's going to take control back into the current limiting side of things. This other one that I've marked as question mark control, this is simply there for other use. So, looking at the circuit, the first thing you're going to be saying to yourself is, well, if I'm not doing anything, you know, or something goes wrong on my control circuitry, or if it's not initialized properly yet, I'm going to get this big spike on the output, because none of these can, if both of these are not pulling the values down, then my output's going to be hard on, and that's not what I want. Well, what you can do here is this other one, and you can add as many control points as you want to here, really, because of the way this works, is you could put this other control point to, say, a power reset circuit. So you can have a simple little op amp with the 5-volt digital control if you're using you know, some digital to analog converter and a microcontroller, or you could use the VREF output as a, you know, through a little bit of an op amp or something, such that until the VREF is above a certain threshold. Remember, you've got plus 15 and you've got minus 15. It's very easy to create a little resistor divider to set some kind of threshold whereby until your charge circuit, and you can use a little RC circuit from your 5-volt reference or something, until it's charged up and now it says, oh, okay, I can release control and allow the power stage to be driven. This could be low, just make it a comparator, not an actual closed loop control. So it's either flat, high, really high, or it's really low. As soon as this goes really high, it will release control from this and allow these other two to take control of it. And as I said, you can put as many of these on as you like. And it's a very, very simple way to allow us to be able to drive that output stage from as many different control circuits as we want without having an issue. And one of the other benefits of this, of course, is I've got V control and I control here that I've put on there. They could be connected to some potentiometers. I could add another 2 V control and I control inputs to this and have those going to a digital to analog converter. So rather than having to have a complex switch, you can simply have, you know, an analog dials on the front of your system, and if you set them to a voltage that's lower than what the computer's trying to get, then you just won't be able to drive that output beyond that. So it will be an easy way of having the a computer controlling the power supply, but being able to set a maximum current and a maximum voltage with a manual potentiometer on the front panel to prevent maybe driving too much power into a sensitive circuit, giving you control. Now, of course, you can equally do that by having the microcontroller with additional digital to analog converters setting like an over voltage protection, over current protection inputs to control this through the analog circuitry, as well as having the normal control. So if you're outputting, you know, whatever well, I guess the scenarios, you can dream up lots of things, but you can put as much control in here as you like. I guess I'm starting to blather on a bit, so I'm just going to move on to the practical demo. So let's get to the breadboard.